OpenAI O1 Preview and OpenAI O1 Mini models are AI models that attached a new process called Chain of Thought (CoT) on top of their existing LLMs such as GPT-4o. For starters, you may want to be familiar with the term CoT. Some people pronounce it CoT. It involves breaking down a request into smaller steps and handling them one by one. It's like an agent that manages various AI models that can include conventional LLMs. The introduction of agentic models like CoT can cause a significant shift in how we interact with AI, reducing the need for extensive prompt engineering or multi-turn conversations. CoT-based models are sometimes called System 2 models. They can offer significant advantages, but there are also challenges to consider. Issues of CoT-based LLMs. 1. Rumination. The main challenge with the current CoT-based LLMs is ruminating, a term proposed here. By ruminating, I mean taking too many extra steps to answer a simple question. Examples of this would be classic problems, such as how many R's are in the word strawberry, or which number is bigger between 2.3 and 2.24, or deciphering obfuscated texts. For a human, it would not take more than a few seconds to get the answer. For conventional computing, letter counting and number comparison can be done with only a few lines of code. Evaluating too many options is not an issue with the transformer used in LLM. This is an issue with the technique used for CoT. 2. CoT won't resolve the transformer's limitations. One study, LLMs with chain of thought are non-causal reasoners, mentions about strange behavior of LLM when combined with CoT. Their findings revealed a surprising frequency of correct answers for faulty CoTs and wrong answers for correct CoTs. This is most likely an issue of the transformer used in LLM rather than CoT. In other words, CoT will not be able to address the fundamental issues of transformer-based LLMs. 3. High cost of training. Another study, Chain of Thoughtlessness, an analysis of CoT and planning, discusses the financial aspect of training CoT by humans. They claim that one of the drawbacks of CoT is the strong trade-off between potential performance gains and the amount of human labor required to develop examples with promising reasoning paths. There can be many different types of reasoning steps for millions of different types of tasks. Training the CoT model for millions of different tasks may take a long time, and many highly qualified human experts. It may only make sense to develop CoT-based AI for select domains to justify the cost if the training cannot avoid human feedback. 4. Social biases. A study. Language models don't always say what they think. Unfaithful explanations in chain of thought prompting found that responses of CoT can still be misleading, especially when it comes to the influence of social biases. They state, our findings indicate that CoT explanations can be plausible yet misleading, which risks increasing our trust in LLMs without guaranteeing their safety. Building more transparent and explainable systems will require either improving CoT faithfulness through targeted efforts or abandoning CoT in favor of alternative methods. 5. Unexpected behaviors. Additionally, there might be cases where CoT managed by reinforcement learning can do something unexpected or even sinister. An example of this would be an RL model beating an opponent in a video game using abnormal methods that humans would not normally use. If unchecked, RL models will not care whether the method is harmful or unfair. Limitations or disadvantages of using RL for managing CoT. OpenAI mention using RL, possibly with human feedback, in their announcement of OpenAI O1 models. RL may be the only thing in the world right now that can effectively prevent a lengthy rumination of evaluating so many scenarios and options. However, here are some limits to using RL for managing CoT. 1. High cost for dynamic environments. Using RL can be very time-consuming and costly, especially in complex and dynamic environments. 2. Suboptimal decisions for rare situations. RL agents may encounter rare or novel situations that are not well represented in the data, leading to suboptimal or risky decisions. 3. Additional training needed for related tasks. RL agents may not be able to reuse or adapt their knowledge and skills to new or related tasks without additional training or fine-tuning. 4. Opaque processes. It may be difficult to trace the logic and reasoning behind the actions and policies of the agents, or to identify the sources of errors or failures. Moreover, it may be challenging to communicate and collaborate with the agents, or to provide feedback or guidance if they are not able to explain or justify their behavior. Strategies for improving CoT-based LLMs such as OpenAI o1. 1. Refine RL for CoT. The design of the reward function is crucial for guiding the model to create effective reasoning chains. It should be carefully designed to incentivize the desired behavior. Balancing exploration, trying new approaches, with exploitation, using known strategies, is important for effective learning. One can consider experimenting with various balancing techniques such as the E-greedy strategy, upper confidence bound algorithm, temporal difference learning methods, Q-learning, SARSA, Bayesian approaches, and deep Q networks. RL can be data hungry, so techniques like curriculum learning or transfer learning can be helpful in reducing the amount of data required. Set a limit for a number of steps or execution time. Gauge the scope of CoT first or during the reasoning process, then respond like, "This is going to take a long time. Do you still want me to continue?" Or, "How long would you want me to evaluate different options?" Stop evaluating options that are taking a long time and avoid time-consuming evaluation steps. Ask users if they want the system to spend more time exploring various options or exploiting existing methods. Develop a fair and reasonable charging mechanism for allocating computational resources to internal reasoning processes, particularly for extended sessions. 2. Implement different CoT agents or models for different cases. Humans can adapt their reasoning style for different occasions, whereas machine learning models follow predefined algorithms. As a result, there might be a need to use different techniques or methods for different types of prompts or sub-processes of CoT. Use different types of CoT. Depending on the status of the user or the purpose of the prompt, you might wish to employ a huge universal CoT agent, a compact CoT agent, or a CoT agent specialized in a certain type of task. Use a small LLM. There are several studies that reported the benefits of using a compact LLM before, during, or after the reasoning processes. You might be able to save resources by using a small LLM instead of a CoT agent for certain cases. Compressing growing prompts using a small LLM can also help. Don't use CoT. There might be simple prompts that can be directly dealt with by existing LLMs or other AI models, such as image, video generation. In this case, simply switch the model temporarily and pass the prompt or a modified prompt to another AI model. Use regular software functions. There might be prompts requesting simple calculations, conversions, counting, replacing, etc. Use traditional functions with regular expressions for these. 3. Use conversion tools. Before passing phrases through the CoT agent or LLM, try turning words into logical expressions, JSON-type representations, CL statements, or custom variables tokens. This method of extracting and rewriting non-literary concepts might be able to increase system performance for reasoning. One can also translate the text into a language that the model is more heavily trained in the area of interest or is less biased. Translating to a language that was trained with more credible information can lead to a less biased response. 4. Run multiple CoTs or steps concurrently. You can try running multiple CoT agents or perform different steps at the same time. The system could dynamically adjust the number of parallel processes based on the task complexity. You might be able to save overall processing time or do a majority vote from diverse perspectives. Combining outputs from multiple agents using ensemble techniques, like boosting or bagging, could lead to more accurate results. Parallel agents can cross-validate each other's work, possibly catching errors or inconsistencies. 5. Develop specific chips for CoT agents. Designing a special chip optimized for CoT could pay off in the long run. This reasoning chip can enhance performance, but also provide a strategic advantage. Embedding core functionalities in hardware could offer protection for your investment in AI development and create barriers to imitation by other companies. To implement a reasoning chip, you might want to consider optimizing circuitry for common CoT operations, e.g., parallel processing, memory access patterns specific to reasoning tasks, as well as including specialized memory structures to efficiently handle the unique data flow in CoT processes. There can be a big potential for significant performance improvements and reduced power consumption compared to general-purpose chips when performing reasoning tasks. However, developing a special chip can be a risky investment, especially if you don't have a competent, multidisciplinary team and necessary resources. As we continue to innovate in this field, we're not just improving algorithms, we're reimagining the very hardware that powers our AI future. Whether you're a developer, researcher, or tech enthusiast, these advancements are shaping the next generation of artificial intelligence. Thanks for watching, and don't forget to like and subscribe for more insights into the world of AI. I'm available for hire also.